Welcome to this coding problem walkthrough. Today, we'll explore problem number 1363, titled Largest Multiple of 3. In this session, we'll dive into the problem requirements, analyze its complexity, and work through an efficient solution. Let's get started. The problem we're solving here is to find the largest multiple of 3 that can be formed by using some or all of the digits in a given array. Each digit in the array is a single number between 0 and 9. The digits can be rearranged in any order to form the result, but there are a few rules to keep in mind. First, the resulting number cannot have leading zeros unless the number itself is 0. If no valid multiple of 3 can be formed, we simply return an empty string. For input, we are given an array of integers, and for output, we need to return the largest possible multiple of 3 as a string. This ensures that the result can represent very large numbers if needed. For example, consider the input array, 8, 1, 9. The digits can be rearranged to form the number 981, which is the largest number divisible by 3 that can be constructed from these digits. So, the output is 981. In another example, if the input array is 8, 6, 7, 1, 0, the digits can be arranged to form 8760. This is the largest valid multiple of 3 that can be made, and it avoids leading zeros. The output in this case is 8760. These examples illustrate the process of rearranging digits to maximize the value while ensuring divisibility by 3. Now, take the input, 1. Here, the only digit is 1, which is not divisible by 3. Since no valid number can be formed, we return an empty string as the output. Another interesting case is the input, 0, 0, 0, 0. In this scenario, all the digits are 0. The largest valid number that can be formed is simply 0, as leading zeros are not allowed in any other case. These examples cover some edge cases where divisibility or the presence of zeros plays a key role in determining the output. Let's look at additional constraints and edge cases. The array can have up to 10,000 digits, and each digit is between 0 and 9. Some edge cases include when all the digits are 0, like 0, 0, 0, where the output is 0. Another common case is when no valid multiple of 3 can be formed, such as with the input, 1, 4, which results in an empty string. If the input is a single digit divisible by 3, like 3, the output is 3. But if the single digit isn't divisible by 3, like 4, the output is empty. Finally, for larger arrays with mixed digits, like 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, the output would be 987, 654, 3210, the largest concatenated number divisible by 3. To solve this, we can use the property that a number is divisible by 3 if the sum of its digits is divisible by 3. This allows us to strategically decide which digits to include. To maximize the number, the digits should first be sorted in descending order and then concatenated. However, if the sum of the digits isn't divisible by 3, adjustments are needed. For example, we might remove 1 or 2 digits, depending on the remainder when the sum is divided by 3. This process ensures that the resulting number is both the largest possible and a valid multiple of 3, while adhering to the problem's constraints. To tackle the problem of finding the largest number divisible by 3, we first consider a brute force approach. The intuition here is straightforward: generate all possible subsets of the given array of digits, concatenate each subset to form a number, and check if it's divisible by 3. From the valid numbers, we would then select the largest one. While this guarantees correctness, it is computationally expensive. Generating all subsets has a time complexity of O2 to the power of n, and sorting each subset to form a number adds an n log n factor, making the overall complexity exponential. Space complexity is also a concern, as storing all subsets requires O2 to the power of n space. For large inputs, this approach becomes infeasible and is therefore not a practical solution. Instead, we can rely on modular arithmetic, which provides a more efficient way to solve the problem. The key observation is that a number's divisibility by 3 depends on the sum of its digits. By modifying the digit set to adjust the sum, we can ensure divisibility and maximize the resulting number. This forms the basis of a more efficient greedy counting approach. The greedy strategy builds on the properties of modular arithmetic to simplify the problem significantly. Instead of generating subsets, we count the frequency of each digit from 0 to 9 and calculate the sum of all digits modulo 3. Based on the remainder of this sum, we can determine the adjustments needed. If the sum modulo 3 equals 1, we remove the smallest digit with a remainder of 1, or if that's not possible, 2 digits with a remainder of 2. Similarly, if the sum modulo 3 equals 2, we remove the smallest digit with a remainder of 2, or 2 digits with a remainder of 1. Once the adjustments are made, the remaining digits are sorted in descending order to maximize the resulting number. This strategy not only avoids the inefficiencies of brute force but also ensures correctness by systematically adjusting the digit set. Finally, special cases, such as when the remaining digits are all zeros, are handled by returning a single zero as the result. This optimized greedy algorithm is both efficient and easy to implement, making it a robust solution. The chosen approach stands out for its efficiency and scalability. By leveraging modular arithmetic and frequency counting, the algorithm achieves a linear time complexity of O(n) for counting and an additional O(k) log k for sorting the remaining digits, where n is the total number of digits and k is the number of digits left after removals. This ensures the method remains efficient even for large input arrays. Its correctness is guaranteed, as the modular arithmetic adjustments ensure that the resulting number is divisible by 3, while sorting ensures the result is as large as possible. Compared to brute force, which is computationally prohibitive, the greedy approach strikes a balance between efficiency and simplicity. While dynamic programming could also solve this problem, it is unnecessary here, as the greedy method is optimal. In summary, the optimized greedy strategy effectively utilizes mathematical insights to deliver a solution that is not only fast but also easy to implement, making it the best choice for this problem. To solve this problem, we need to determine the largest number that can be formed from a subset of the given digits such that the number is divisible by 3. The key principle here is the rule of divisibility for 3. A number is divisible by 3 if the sum of its digits is divisible by 3. This forms the foundation of our approach. First, we calculate the total sum of all digits in the array, which we'll call S. If this sum is already divisible by 3, we can directly use all the digits to form the largest possible number. However, if S is not divisible by 3, we must adjust the subset of digits to make the sum divisible by 3, which we'll explore further in the next steps. Now that we understand the importance of the sum's divisibility by 3, the next step is to categorize the digits based on their remainders when divided by 3. This gives us 3 groups: Group R0 for digits with a remainder of 0, Group R1 for digits with a remainder of 1, and Group R2 for digits with a remainder of 2. This categorization is crucial because it allows us to strategically decide which digits to remove to adjust the sum. If the sum, S, leaves a remainder of 1 when divided by 3, we have 2 options: either remove the smallest digit from Group R1, or remove 2 of the smallest digits from Group R2. Similarly, if S leaves a remainder of 2, we can either remove the smallest digit from Group R2, or 2 of the smallest digits from Group R1. The goal in both cases is to minimize the removal of digits, prioritizing smaller digits so that the remaining set can form the largest possible number. After adjusting the sum to make it divisible by 3, the next step is to form the largest number with the remaining digits. To do this, we combine all the remaining digits from the 3 groups and sort them in descending order. This ensures that the final number is as large as possible. It's important to handle edge cases here. For instance, if all digits are removed during the adjustment process, the output should simply be 0. Similarly, if the input consists entirely of zeros, the output is also 0. The key insight here is that the problem revolves around the divisibility rule for 3, focusing on the sum of digits rather than their order. By removing the smallest possible digits and sorting in descending order at the end, we ensure the optimal solution. Arrays or lists are used to store the digits and categorize them, while sorting and a greedy approach help maximize the resulting number. The key operations in this algorithm include calculating the sum of the digits, which takes O(n), and categorizing the digits into the 3 groups based on their remainders, which is also O(n). Sorting the remaining digits to form the largest number requires O(n) log n, making this the most time-intensive step. Overall, the time complexity of the algorithm is O(n) log n, while the space complexity is O(n) due to the storage of digits in groups. It's also important to consider several edge cases. For example, if the input consists solely of zeros, the output should be 0. If no subset of digits can make the sum divisible by 3, the output is also 0. If the input is empty, the output is 0 as well. Finally, if the input contains just one digit, the output will either be the digit itself if it's divisible by 3, or 0 otherwise. These edge cases ensure that the algorithm is robust and handles all possible inputs correctly. To solve the problem of finding the largest multiple of 3 from a list of digits, we start by importing the counter class from the collections module. This allows us to count the frequency of each digit efficiently. Inside the solution class, we define the method largest multiple of 3, which takes a list of digits as input. The first step is to count the frequency of each digit using the counter and calculate the total sum of all digits. Here, the total sum is computed by multiplying each digit by its frequency and summing these products. Next, we define a helper function called remove_digits. This function is designed to remove a specified number of digits with a given remainder when divided by 3. It iterates through the digits, starting from the smallest, and decreases their count while reducing the number of digits we still need to remove. This ensures that we adjust the total sum in a way that makes it divisible by 3. Now, we check the remainder of the total sum when divided by 3. If the remainder is 1, we attempt to remove one digit with a remainder of 1. If that's not possible, we remove two digits with a remainder of 2. Similarly, if the remainder is 2, we first try to remove one digit with a remainder of 2, and if that fails, we remove two digits with a remainder of 1. This adjustment step ensures that the sum becomes divisible by 3. After adjusting the digits to make the total sum a multiple of 3, we need to construct the largest possible number. To do this, we iterate through the digits in descending order, from 9 to 0, and append each digit to the result string as many times as its frequency in the updated count. This ensures that the resulting number is as large as possible. Finally, we handle a special edge case where all the remaining digits are zeros. In this scenario, the constructed result might still contain multiple zeros, so we check if the result starts with 0. If it does, we return a single 0 instead to represent the valid number. Otherwise, we return the constructed result. This completes the implementation, ensuring that the output is the largest number divisible by 3 formed from the given digits. Here, we begin by importing the necessary utilities and defining our class and method. The goal is to find the largest number that is a multiple of 3 from the given digits. To do this, we start by counting the frequency of each digit from 0 to 9 using an array called count. We also calculate the total sum of the digits as we iterate through the input array. This total sum will help us determine whether we need to adjust the digits later to make the number divisible by 3. Next, we define a helper method called remove_digits. This method is designed to remove a specified number of digits that leave a given remainder when divided by 3. It loops through the digits, checking if their modulo result matches the target remainder, and then removes as many digits as needed, up to the specified limit. If the required number of digits is successfully removed, the method returns true, otherwise, it returns false. This setup prepares us to adjust the total sum as needed in the next steps. Now, we adjust the total sum to ensure it becomes a multiple of 3. If the total sum leaves a remainder of 1 when divided by 3, we first attempt to remove one digit with a remainder of 1. If that's not possible, we try removing two digits with a remainder of 2 instead. Similarly, if the total sum leaves a remainder of 2, we first attempt to remove one digit with a remainder of 2, and if that fails, we remove two digits with a remainder of 1. Once the total sum is adjusted, we move on to constructing the largest possible number using the remaining digits. To do this, we iterate through the digits from 9 down to 0, appending each digit to a string builder as many times as it appears in the count array. Finally, we handle the edge case where the result might consist entirely of zeros. If the first character is 0, we return 0 directly, otherwise, we convert the string builder to a string and return it as the result. This ensures the output is the largest number that is a multiple of 3, or 0 if no such number can be formed. To solve the problem, we start by analyzing the input digits 8, 1, 7, 6, 0. First, we calculate the frequency count of each digit using a counter. This gives us 8, 1, 1, 1, 7, 1, 6, 1, 0, 1, meaning each digit appears exactly once. Next, we compute the total sum of all the digits, which is 8 plus 1 plus 7 plus 6 plus 0 equals 22. Now, we check the remainder when this total sum is divided by 3. Since 22% 3 equals 1, the sum is not divisible by 3, and we need to adjust it. To make the sum divisible by 3, we can remove one digit with a remainder of 1. Looking at the digits, the only candidate is 1. Removing this digit updates the frequency count to 8, 1, 1 o'clock, 7, 1, 6, 1, 0, 1, and the total sum to 22, 1 equals 21. Now, 21% 3 equals 0, so the sum is divisible by 3, and we can proceed. With a sum that is now divisible by 3, we move on to building the largest possible number. To do this, we sort the remaining digits, 8, 7, 6, 0, in descending order. Once sorted, we concatenate these digits into a single string, resulting in 8760. This is the largest number that meets the requirements for this input. Next, let's consider another example with the input digits 3, 6, 9, 0, 0. Here, the frequency count of the digits is 3, 1, 6, 1, 9, 1, 0, 2. The total sum is 3 plus 6 plus 9 plus 0 equals 18. Checking the remainder, we find 18% 3 equals 0. Since the sum is already divisible by 3, no adjustments are needed. In this case, where the sum is already divisible by 3, we can directly focus on building the largest number. The digits 3, 6, 9, 0, 0 are sorted in descending order to become 9, 6, 3, 0, 0. Concatenating these digits results in the output 96300. Finally, let's analyze another example with the input 0, 0, 0. Here, the frequency count is 0, 3, and the total sum is 0 plus 0 equals 0. Since 0% 3 equals 0, the sum is already divisible by 3. With only zeros in the input, concatenating them produces the string 0, which is the largest valid number for this case. Here, we analyze the time complexity of the solution by breaking it down into distinct steps. First, we count the frequency of each digit using the counter class. This operation requires iterating through the input array, which has a length of n, making this step O, n. Next, we calculate the total sum of all digits, weighted by their frequencies. Since the range of digits is fixed between 0 and 9, this involves a constant number of iterations, with each iteration taking O1. As a result, this step is O1. Then, we look at the adjustment process where we remove digits to ensure the sum is divisible by 3. The removal process involves iterating over a constant range of digits, and since at most 2 digits are removed, this step is also O1. Together, these steps give us an efficient start to the solution. Now we consider the time complexity of building the final result. This involves iterating through the digits in descending order, from 9 to 0, and appending each digit to the result based on its frequency. Since the total number of digits is proportional to n, this operation takes O(n) time. When we combine all the steps, the overall time complexity of the solution is O(n). Although some steps involve constant time operations, the counting and result construction steps scale linearly with the input size. Shifting to space complexity, we start by looking at the storage required for the frequency count. The counter object holds the frequency of each digit, and since there are only 10 possible digits, this requires O1 space. Additionally, variables like total_sum and the helper function remove digits use a constant amount of space, which also contributes O1. The next aspect of space complexity is the construction of the result string. In the worst case, the result contains all digits from the input array, so this step requires O(n) space. When we combine the storage for the counter object, the intermediate variables, and the result string, the overall space complexity of the solution is O(n). To put this into perspective, we compare it to a naive approach. A brute force solution would generate all permutations of the input digits, check each permutation for divisibility by 3, and select the largest valid one. This process has a factorial time complexity, O, n, and checking each permutation adds O, n, for each case, resulting in O, n. Asterisk n. In contrast, the optimized approach avoids generating permutations by leveraging the mathematical properties of numbers divisible by 3. It uses a minimal adjustment strategy to achieve O, n, time complexity, making it exponentially faster than the naive solution. Finally, let's evaluate the best, average, and worst-case scenarios. In the best case, all digits already form a number divisible by 3. The solution only needs to perform frequency counting and result construction, both of which take O, n, time. In the average case, a small number of digits need adjustment to make the sum divisible by 3. Since the adjustment step is constant time, the overall complexity remains O, n. Even in the worst case, when most digits are removed or adjusted, the operations are still bounded by O, n, because the adjustment process is independent of the input size. To summarize, this solution is highly efficient, with both time and space complexity of O, n. It avoids the inefficiencies of a brute force approach and scales effectively, making it well suited for handling large inputs. One of the most common mistakes when solving this problem is ignoring edge cases. For example, if the input array is empty or contains only zeros, such as 0, 0, 0, it's easy to overlook that these cases should still yield a valid result, specifically 0. Neglecting edge cases like these can lead to runtime errors or incorrect outputs during evaluation. Another frequent issue is misapplying the modulo operator when combining digits. Instead of forming the number correctly, some solutions treat the digits as individual values, such as interpreting 123 as 1 plus 2 plus 3. To ensure correctness, the modulo operation must be applied to the fully concatenated number. Additionally, handling large numbers inefficiently is another pitfall. For instance, directly generating and storing all possible subsets and concatenations can quickly lead to memory overflow, especially with larger inputs, due to the exponential growth of subsets. Lastly, overlooking leading zeros is a critical error. Numbers like 0, 1 are invalid, so if leading zeros aren't properly handled, the solution can produce incorrect outputs. Each of these mistakes emphasizes the importance of a thoughtful and efficient approach to edge cases and constraints. Another major mistake is failing to optimize for divisibility by 3. Instead of leveraging the properties of numbers divisible by 3, such as their digit sums being divisible by 3, some solutions check divisibility for all subsets, leading to unnecessary calculations and inefficiency. To address this, it's crucial to understand a key insight for this problem. A number is divisible by 3 if and only if the sum of its digits is divisible by 3. Using this property can significantly reduce the problem's complexity. An optimal approach might involve dynamic programming or modular arithmetic. For example, you can maintain subsets based on their modulo classes 0, 1, or 2 rather than brute forcing through all possible subsets. Brute force may seem easy to implement, but it's highly inefficient for large inputs, with a time complexity of O, 2 to the power of n. By comparison, an optimized modulo approach reduces this to O, n asterisk m, where n is the number of digits and m is the number of modulo classes, which is just 3 in this case. A practical tip is to always clarify edge cases with the interviewer before starting, especially scenarios involving arrays of zeros or non-unique digits, to ensure your solution aligns with the problem's expectations. This problem is closely related to several other LeetCode challenges that involve similar concepts. For instance, LeetCode 1262, greatest sum divisible by 3, also deals with modular arithmetic and optimizing subsets. LeetCode 416, partition equals subset sum, and LeetCode 698, partition to k equals some subsets, test your understanding of subset sums in dynamic programming. Finally, LeetCode 518, coin change 2, explores ways to generate combinations that meet specific criteria, which can be helpful in understanding how to approach subset problems systematically. When considering alternative approaches, a greedy algorithm can be used to pick subsets quickly, but it may fail for certain edge cases due to its lack of robustness. Backtracking is another option. It generates subsets recursively while pruning invalid paths, which makes it easier to implement than dynamic programming. However, it's slower for large inputs. A more reliable approach is dynamic programming, where you use a DP table to track the modulo classes for subsets. This method is optimal in terms of time complexity, but it demands careful implementation and additional space. Each approach comes with trade-offs, so it's important to weigh their pros and cons based on the problem's constraints. To wrap things up, focus on recognizing patterns in the problem, such as the properties of numbers divisible by 3. These insights can help you simplify the problem and choose the most effective approach. During interviews, it's crucial to balance efficiency and clarity. While optimizing your solution, make sure you can clearly explain your thought process and justify the trade-offs in your approach. For example, if you choose dynamic programming over a greedy method, articulate why it's more reliable for edge cases. Finally, always communicate with your interviewer to clarify edge cases or validate assumptions. This not only demonstrates your problem-solving skills but also shows that you're thorough and methodical in your approach, which is just as important as arriving at the correct solution. Great job working through this problem. In summary, we tackled problem number 1363 using sorting, modular arithmetic, and a greedy approach to maximize efficiency. Remember to practice these concepts to strengthen your problem-solving skills. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!